Hey there, chemistry students. This is Miss Ruark. This is the first vodcast of the year, and it's vodcast 1.1 where we're going to cover atomic structure. This is how you're going to get your notes. Remember, I don't lecture in class, but I do give these, and these are what you're going to come home. And what would cover a typical lecture in class, I can do in a short amount of time at home, where you watch this and fill in your notes. So as you go along, make sure you're listening. Some of the things that are going to be answers will be, or things that you'll have to write down will be said, and some of the things that you'll write down will be written down as well. So make sure that you're paying attention and listening to the vodcast. While we're going, if at any time you don't get something, feel free to pause it, rewind it, watch it again. These things will be up all year long for you to use. All right, so atomic structure. First off, we've got to talk about an atom. So what in the world is an atom? Well, we know that the atom is the smallest particle of, let's see if I've got, is my pen working? Where's my mouse? There it is. Oh, there we go. All right, it's the smallest particle of an element that retains its properties in a chemical reaction. Okay, this is the smallest part of an element that retains its properties in a chemical reaction. And just to give you a little bit of history on it, not a lot, but the first guy who suggested the existence of the atom was this Greek old dude right here. Oh yeah, good job. His name is Democritus. Okay, he was from ancient Greece. He was around 460 BC to 370 BC, and he said that all matter consists of tiny, indivisible, unchangeable particles called atoms. Okay, the word atom came from the Greek word atomos, which was atom. Okay, Greek dude, Greek word, atoms. Okay, and then for about 200 years, nobody believed him. Okay, and we'll talk more about that when we get into the history of the period or the atomic or the theory of the atom and how it's evolved over time. But this guy right here, old English dude, right? He was an English teacher, not an English teacher, but he was a science teacher who happened to be English, and he lived around 1800s, and his name was John Dalton, and he came up with Dalton's atomic theory, which says all elements are composed of um, tiny atoms. Sorry, not tiny atoms. I don't know what I was trying to put there. Tiny particles. Shouldn't be there. Tiny particles called atoms. I don't know what I was trying to put there. All right, atoms of the same element are similar, and atoms of different elements can combine to form compounds. Okay, and then the last thing that he said is that chemical changes or chemical reactions occur when atoms are separated, joined, or rearranged. Okay, now remember, this guy didn't just sit down and think all of this up overnight. Okay, he came up with this theory based on lots of research that was done by tons of other scientists throughout the years and throughout the ages. Okay, so how do we distinguish between atoms? How is an atom of hydrogen different from an atom of oxygen? Well, they're different because elements contain different numbers of protons. Okay, protons. And the symbol for a proton is a P with a plus as a superscript. Okay, protons, that is called the atomic number, and the atomic number is the number of protons in the nucleus of an atom of that element. Okay, every single element has a particular number of protons. So the carbon has 6 protons. No other element has 6 protons. Nitrogen has 7, hydrogen has 1, oxygen has 8. No other element has that same number of protons. Okay, and then we have other, okay, so let's talk about the subatomic particles. We have protons. Okay, we just talked about those. Protons are positively charged, and found inside the nucleus of the atom. Okay, the symbol for a proton is that P with a superscript P or plus. It has a charge of positive. It's a positive charge. Charge of positive. That doesn't make any sense. It has a positive charge. And the mass is really, really small, but we need to be able to count it. So we say it has a relative mass of 1. Okay? And remember, always has the same number as, or the number of protons is always the same as the atomic number. It's actually the same thing. Okay, also inside of that nucleus we have neutrons. And neutrons are neutral. Neutron, neutral, sounds the same. Neutral particles found inside the nucleus of an atom, and the symbol for that is N with a 0 up top, okay? So because there's no charge, right? Has a charge of nothing. There is no charge. Its mass is pretty much going to be the same as a proton. And because the mass is similar, and we gave the mass of a proton 1, we would say that the mass of a neutron is 1. All right, and you don't just know the number of neutrons in an atom, you actually have to calculate the number of neutrons in an atom. Okay, so how do we do that? Well, to do that, we have to take this number called a mass number. And the mass number is usually, it's going to be a whole number, and the mass number is equal to the atomic number. Okay, let me write this to the side here. Mass number is equal to protons plus neutrons. All right, well, if protons is atomic number, it would be atomic number plus neutrons. All right, so to figure out the number of neutrons, mass number minus atomic number gives us neutrons. How many neutrons are in an average cobalt atom? Well, in order to see that, let's see if I'll be able to get my little, I know there's a way. Hold on, I'm going to switch to my pointer. Okay. Let me switch. Control A should give me, it didn't. Let's try it again. It doesn't like me. Okay, well, if we looked at our periodic table, I'll just go forward a page. If we look at our periodic table, here we go. Cobalt is right here. All right, now, in the periodic table, we have some information. We have a number here at the top, and that number is our atomic number. Okay, and we'll talk more in depth about this in the next vodcast, but that tells us our atomic number. So our atomic number for cobalt, if you can read that, is 27. I'm going to erase all that. Okay, so 27 is our atomic number. Now, if we aren't given a mass number for an element, we have to look at the periodic table to get that mass number. And we look here at this bottom part which says atomic mass. Now, it's a number that's decimal form. So what we're going to do is we're going to take it and round it to the nearest whole number. So 58, let me write it up here, 58.933 rounds to 59 as our mass number. And we only do that if the mass number is not given. Okay, so let's go back and we set, oh, I forgot it already, 27. So we have 27 protons, and we have a mass number of 59. All right, so to figure out the number of neutrons, we would take the mass number, which is 59, and we subtract the number of protons, or the atomic number, from that. So 59 minus 27, you should have 32, and that should be 32 neutrons in an average atom of cobalt. All right, so gold. Let's look at gold. All right, gold is here. AU, right? Gold. It has 79 protons. All right, so it has 79 protons. And look here. You're going to learn this in the next podcast, but here it tells us that, look, we have a mass number of 197. So we're going to take our mass number, 197, and we're going to subtract from that our atomic number, which is 79. And I don't have a calculator with me, so 7, 9, that would be 8. This becomes an 8. I know, I'm having to do the math. 118. Hopefully I did that right. So we should have 118 neutrons in an average atom of gold. Not too bad. Okay. More subatomic particles. We also have things called electrons. These are some freaky little boogers, okay? These little guys are negatively charged, and they're all around the outside of the nucleus. They're pretty crazy. They move really fast, and they have a mind of their own. All right, so they're found outside the nucleus of an atom. Outside the nucleus of an atom, they have a charge. It's a negative charge. They are negative charge. And guess what? Their mass is so small in comparison to a proton and a neutron that we say they have no mass, zero mass. All right? Okay, so to give you a visual of this, let's say that you go to the doctor and he tells you to get on the scale. So you get on the scale and he finds your weight. And then you get off the scale and you rub your eye and you realize, oh my gosh, I just lost an eyelash. And you go, doctor, wait. Take my mass again. You gotta get my weight again. I just lost an eyelash. It's going to change drastically. The doctor's probably going to look at you and laugh or have you committed, right? Because an eyelash isn't going to change your weight. You're still going to weigh the same. Okay, well, think of the electrons as an eyelash. If those electrons are so light in mass that they don't affect the mass of the atoms. So we say that the mass of them is negligible, which means it doesn't matter. Okay, so if they're extremely light and they have no mass in comparison, well, why do they stay around the nucleus? Well, the reason they stay around the nucleus is because opposites attract. Okay, if nothing else gets you through this class, remember, opposites attract. Okay, inside this nucleus, you have positive charges all over the place, and then you have these negatives floating around all over the place. There's an attractive force here between these two that's pulling them closer and closer. Okay, so the positives and the negatives. The reason it doesn't go all the way in is because it's moving so fast, it's not going to go inside. Okay, so it's being held out. All right, so that I think that sums it up. And I'm going to leave you with something to kind of smirk about at the end of every vodcast. And, well, I'll see you in class.